but then we're like, we don't get considered A. Like, we missed the cut. So we're taking.
All right, so consider this function, 2 times 4 to the x. The table below shows some selected values of x. All right, so 4 to the x, that gets really big really fast, right? Like at x equals 7, we're all the way at 32,768. So graphing this would be problematic maybe, or you'd need a really long y-axis. And even if you did put your y-axis to 30,000, so there would be 20,000, and there's 10,000. Like, all of your other points are so far below 10,000, it would hardly be worth graphing. You wouldn't see very much. So these huge numbers kind of present a problem if we're going to graph like we normally graph. So somebody came up with this idea of, let's do a semi-log plot. So basically our y scale goes up by a power of 10 each time, rather than the normal, 1, 2, 3, 4, or even 10, 20, 30, 40, or even 10,000, 20,000, 30,000. Like, we're going up by powers of 10. And now let's graph those points and see what happens. So 0, 2, 0, 2. Again, this is weird looking, but roll with it. 0, 2, 1, 8. 232. So again, you get careful with the scale. Once I hit 10, those markers are 10, 20, 30. So 32. 3, 128. So 100. But that next marker is 200. So I definitely don't want to get all the way up to 200. 128, somewhere in there. 4, 512. So 100, but then I'm counting by hundreds in this little region here. So 100, 200, 300, 400, 500. And again, 500 is not in between 100 and 1,000 because the scale is kind of wacky. 5, 2,000. All right, the 47 is not going to matter a whole lot, right? Just a little bit more than 2,000. 6, 8,000. 2, 3, 4, 5, 6, 7, 8, somewhere up in there. And then 7, 32,000. So this was 10,000, 20,000, 30,000. So 32,000, my best guess there. Okay, well, conclusion, you already see it, I think. It's a line. Be careful when you say it's a line, because it's not a line, but it looks like a line. So be careful how you phrase that. We can play connect the dots here. It should be perfectly linear. Now, it may not be exactly linear because graphing by hand on semi-log paper is kind of tricky, but it should be exactly linear on this graph. Again, be very careful how you phrase that. That function is not linear, but it appears linear on the semi-log graph paper. So what do you notice? Like, this is exactly what you said. Exponential graphs, I'm going to say appear linear. I think that's the best word choice there. Appear linear on a semi-log plot. Starred, circled, underlined, or whatever you need to do to remind yourself that that's super important. Super important because there's not a ton of stuff we can really do with this. It's like when you first learn something, it's like you realize you're just scratching the surface. And so I can't ask a ton of hard questions about it because we're just now learning this semi-log plot thing. A bunch of questions can be answered by understanding that exponential graphs look linear on a semi-log plot. Okay, now we get to a little bit more algebra math stuff here. Write log base 4 of f of x in the form log base 4 of f of x equals mx plus b. Okay, well that seems a little bit weird, but let's write f of x. Start with that. 2 times 4 to the x. It's the same f of x we started with at the very top. And if we want log base 4 of that, well, let's log base 4 both sides. Okay, and I'm trying to match up, right? It says put it in this format, so I'm trying to match that form. So I've got the left-hand side done. Right? The left-hand side looks like it's supposed to look. Now I'm supposed to somehow mess with the right-hand side so that it looks like that. This would be log properties. If I raise it to the e, or if I raise it to the 4, that would be okay, but it would put me right back to here, right? Yeah. So it wouldn't be wrong, it would just be spinning my wheels there, going in circles. Instead, let's split this up. Log base 4 of 2 plus log base 4 of 4 to the x. Right? Log properties. But log base 4 of 2, I can figure that out. Like that's the fishhook thing. 4 to what would give me 2? Yeah, not negative, just the 1/2. Because 4 to the 1/2 is 2. And then on the second one, we take that x down front. X times log base 4 of 4. But what's log base 4 of 4? 1. So this is 1/2 plus x. Which I guess is pretty much right, but if it wants the mx first, then I guess we should write x plus 1/2. And now this is like we turned it into like the algebra 1 equation, y equals mx plus b. So m is 1 and b is 1/2. Okay, graph this relation with log base 4 f of x as the vertical axis. So that means log base 4 of f of x. That's our y. So we're now just graphing y equals mx plus b. So we did a bunch of log property things to turn it into a line. Let's see. How long has it been since you graphed a line? We began at the 1/2. And then our slope is 1, so up 1 over 1. So it's kind of weird that those two graphs are showing the same information. One of them, the log is taken care of on the graph. The graph paper has the log sort of built in. On this one, the y-axis was log base 4 of f of x. They both dealt with the log kind of different ways. Both linear. Well, they both appear linear, I guess I should say. The graph is linear. All right, example 1, kind of the same thing. Given that 9 times 3 to the 2x, find the values of m and b, so again the mx plus b thing, such that log base 3 of g of x equals mx plus b. Again, the problems are worded to kind of get you started. So like if you want log base 3 of g of x, well, let's take log base 3 of both sides. So I've got my left-hand side is done. Now I need to use my algebra properties on the right-hand side to get it to look like mx plus b. So I'm going to hit pause because I think you know how to do this. So we began at 2, and our slope is up 2 over 1. And so there's our graph, but we should probably label our y-axis because it's not just y, it's log base 3 of g of x is what we're graphing. So it appears linear because we took the log of both sides. Number 2, kind of the same thing but with natural log. Find the values of m and b such that natural log of h of x equals mx plus b. So again, it's telling you what to do. Take the natural log of h of x, so again, the left side's done, right? Maybe it feels weird that your answer is in the form of natural log of h of x, but that's what it wants you to do. Answer it fully. So that's kind of it. It's weird, it's different, but it's only one thing. In the above 2 examples, we know the base of the exponents, so we can graph using the grid in example 1, like a regular looking graph. But if we just have a set of data, we don't know the base, then it's difficult, like we can't do what we've been doing. So instead, we're going to graph and then kind of work backwards to see if we can figure out what m and b are. Actually, I don't even think.
I need the old ones back.
Okay. Okay, so this one we're starting with the data. So I don't know what the base is. So let's just graph those and graph the data. Label your axes, and then let's figure out what's going on from there. So 0, 0.2, 2, 1.1, 4. Oh, we skipped to 4. Be careful, we don't have a 3 on there. 4, I said be careful, and I put 1 in the wrong spot. 0.2, 2, 1.1, 4, 5.6. So 2, 3, 4, 5.6. 5, 12.8, 11, 12.8, 6, 29.4. So, oh, I put 12.8 in the wrong spot because I was looking at the wrong thing. That's why you do math in pencil. 2030, so there's 29.4. Plus, I'm expecting this to be linear, so I kind of have a built-in check. If something looks way out of whack, I'm making sure I put it in the right spot. 20, 30, 40, 50, 60, 70. 8, 155. 100, 200, so I need to be in between there. Nope. 10, 8, 19. 200, 300, 400, 500, 600, 700, 800, so like way up toward the top, almost to 1,000. 12, 4,300, 1,000, 2,000, 3,000, 4,000, and a little bit more. Again, the 0.8 doesn't matter hardly at all when it comes to graphing that thing, because you're in the 4,000s. And then 13, comma, almost 10,000, like almost at the top. And we can fit a line to that. This one may not be perfectly linear because this is probably data you took in a physics experiment, right? And so there's other things going on, so it doesn't end up perfect, but it ends up pretty close to a line. What does this graph say about the data? Well, I'm going to say it this way. The graph is linear, but it's a semi-log graph. So what does it say about the data? The data is exponential. So be super careful about linear versus exponential. The graph, yes, that's linear. But it's linear because the data was exponential. And then approximate the values of f of 3. Well, I'm just going to look, and we're going to all have slightly different answers for this. 1, 2, almost 3. So I'm going to say 2.8, but I don't know. It depends on the line you drew. F of 9. 100, 200, 300. I'm going to say I better put some approximates on there because that's not exactly right. And because it's a log graph, you could be off by 100 and still be okay. Right? It feels weird to say that 300 and 400, it's close enough. But on a log graph, it is close enough. So, or 200. Again, it feels weird to think that 200, 300, 400, it's all the same. Well, on a log graph, when you're going up to 10,000, it is kind of close to the same.
Good morning, Kingwood.
Perfect timing.